Okay, we are off to looks like chapter 7. I think last time we finished up chapter 6 and talked in terms of bonding. So here in chapter 7, we're going to talk about chemical reactions, types of reactions, and then we'll also talk about some calculations that you could do from the equation, which is known as stoichiometry. So let us get started here. So we're going to start with really balancing equations and writing equations. So when we look up here, this is a balanced chemical equation. Whenever we use a chemical equation, we want to make sure that it is always balanced. And what that means is we have the same number of elements on each side of the arrow. That is based on the law of conservation of mass, which means that we do not create nor destroy any elements in a chemical reaction. Really, the only thing that's happening is we're really breaking bonds on everything that we start with, and we're making new bonds on everything that we make on the product side. That only involves electrons. It involves nothing in the nucleus or anything like that, protons or neutrons, and that means that we never lose any elements along the way. So in a chemical reaction, if you start with six carbons, you should end with 6 carbons. And again, they just may be in different compounds along the way. The only time we really ever do change elements is more in nuclear reactions, which we don't talk about, which was chapter 5. In those, we do nothing but change the elements. But in what we deal with here, which are chemical reactions, we never ever change the elements. So we always have the same number of elements. And when we look at something like this is a balanced equation. And if we look at why it's balanced, it is if we take the coefficients here, that's a 2 here, a 1, and a 2. If we look at just the hydrogen on the left-hand side, we have 2 times 2, so we do multiply those two together, and that would give us 4 hydrogens on the left-hand side of the arrow. The coefficient is not written here, so it's assumed to be a 1, and basically 1 times 2 is 2 for our oxygen. And if we go to the right-hand side and do the same thing for each element, we have that 2 that goes to the hydrogen, which should be 2 times 2 is 4. And that 2 in front also goes to the other element that's there. And remember that if there's nothing written here, it's assumed to be 1, and that would get us our 2 oxygens. So we have, again, the same number of hydrogens on each side, the same number of oxygens on each side, and this would be a balanced equation. When we look at an equation, it contains basically 2 parts. The first part are the reactants. That's on the left-hand side of the arrow. So everybody on the left-hand side here are reactants. It's really your starting material in a chemical reaction. Pretty much all those reactants are going to break apart, going to break all their bonds, going to let all the elements kind of go free in a sense. And those elements will recombine on the other side of the arrow, which are the products. So the products are on the right-hand side of the arrow. And those are obviously the substances that are formed as a result of a chemical reaction. Once again, here we don't change any elements. We have the same elements that we started with, just arranged in different compounds on the product side to produce new compounds. This is a chemical change because what we start with and what we end with are 2 different things fundamentally, and that's basically what a chemical reaction is. Now, there are some other things that you sometimes will see written in the equation, and for example, you will oftentimes see next to the formulas the states of everybody. So some people may have an S for solid, some may have an L for liquid, G for gas, and also AQ, which is aqueous, and that's a water environment. That's really a solution, is what that is. Now, there is a difference between, say, liquid and aqueous, and sometimes people maybe do not understand the difference. A liquid is a pure substance. So, for example, if you had water all by itself, that would be considered a liquid. Okay. Now, if you took water, which is a liquid, and you mixed it with some sodium chloride, which is a solid, these two guys will actually dissolve. Actually, the sodium chloride will dissolve. So basically, the salt will dissolve in the water. And what will happen is you will create a sodium chloride solution that is known as aqueous. And that is a solution, which is actually a homogeneous mixture, basically. So a solution is really two or more things that basically dissolve in each other, looks the same throughout. And that is the difference between AQ, which is aqueous, and L, which is liquid, which is just one thing by itself, like water, just a pure substance, nothing else with it. They both are in the liquid state, and that's what sometimes confuses people because they both look like liquids, obviously. But again, one is really a mixture, and one is just a pure substance by itself, which is that liquid. Other things that you sometimes will see in equations written do fall like a lot of times written right on top of the arrow, and a lot of times you will see a catalyst written there. And a catalyst is not a reactant. It's not a product. And most importantly as well, I'll come down here, it does not get used up in the reaction. Really what a catalyst is there for is, in most cases, it is added to speed up the reaction. So that is most of the time why you add basically a catalyst, is to basically speed up the reaction. We won't get too far into what catalysts do or does or how they work, but essentially what they're able to do is find a more efficient way for that reaction to take place. And by finding a more efficient way for that reaction to take place, it allows the reaction actually to occur a lot faster than it would if the catalyst wasn't there. For example, sometimes catalysts are very oftentimes metals. So for example, if you had some gas molecules flying around, and if they were just flying around by themselves without the catalyst present, it would take a little bit of time for them to find each other, to start reacting and stuff like that. You could sometimes speed this process up by putting like a metal catalyst in there. And what that does sometimes is it attracts the gas molecules towards the metal itself, and that allows them to come in contact with each other a lot faster than they would if they were just kind of flying around trying to find each other. And it also sometimes will help in sort of the process of them starting to break bonds and make bonds and stuff like that. So a catalyst typically will be something that is allowing the reaction to sort of occur a lot more efficiently than it normally would without it. But it's not considered a reactant nor a product. There are a lot of reactions, for example, that will happen, and you'll wait forever for it to happen, but it will eventually happen. They're very, very slow. And a lot of times we want to add catalysts to kind of speed up the process. For example, like making ammonia is a really, really slow reaction, but it will eventually happen. But if you add a catalyst to it, it will make a much more faster and efficient type reaction. So a lot of times on top of the arrow is where you'll see these catalysts written, things like, for example, metals like platinum. Sometimes you might even see like an H plus, and an H plus indicates that some type of acid is being used as a catalyst. So those are very common things that you'll see sort of in equations. Any questions on that? Did I get the second zero? On this side you're talking?
Yeah, very top.
Yeah. On the other side, on the right? Yeah. It's because this coefficient that's in front, it goes for everybody that's behind it, all the elements. So we will multiply that 2 by the 2 hydrogens that are there in the formula. And then basically this 2 would also be multiplied over here. When there's nothing written in the formula, it's assumed to be a 1. So basically it's 2 times 1. Yeah. Other questions? Okay. So let's talk about balancing equations. And frankly, I don't know, most people go trial by error, but we'll talk about some ways to, I guess, sort of do it. First off, though, if you have any type of equation that's given to you in words, for example, just like words instead of actual formulas, it's really, really important to make sure that you start with the correct formulas. So you want to make sure you write the formulas down correctly, like you're doing like nomenclature type of deal, and start with all the right formulas. If you do not start with the right formulas, you'll be there all day trying to balance something that will never balance because you don't have the right formulas. That's a very common mistake that people make. I would say more commonly that mistake happens when there are certain situations where you may be given just the reactants and not the products, and you have to kind of like figure out what goes on the product side, for example. And a lot of times what people try to do is this, and it may not make sense to you right now, but as we go through it, maybe it will make some sense. They try to write the formulas of what's on the product side and balance the equation at the same time. And that is the incorrect way to do it, because you usually will again end up with the wrong formula and you'll be there all day trying to balance something that will not balance. So if you ever need to sort of predict what's on the product side and write formulas, that is the order at which you want to do it. You want to first get all the correct formulas on the right-hand side of the arrow, regardless of the balancing part of it. Once you have all the correct formulas, then you should go back and balance it. So you never want to try to do those things together. And again, that's a very common error that people make. They try to kind of do both of them. They look on the left and go, oh, wait, there's two of those, so I probably should just make a two here to try to balance it as they're trying to write the formulas. So the order should always be everything down there correctly in terms of formulas. Everything's correct, just like you were doing like nomenclature and writing formulas. Then you should go back and balance. So that's always the way you want to do it. Once you do that, we want to balance the equation. And when we balance the equation, the only thing that we change are the coefficients. And those are the numbers that are in front. So we never, ever change any of the subscripts. So, if you had like H2O, we never change that, because if I change that to, is it still water? It is not. It's made whatever I made there, probably something that doesn't exist. So we never change those numbers. We never as well do anything weird like put a number between things. We don't do any of those things. So it is only when you're balancing the numbers that come in front, which are the coefficients, that you should change. You want to start with maybe the most complicated. I personally start with what looks kind of like the simplest to fix in terms of balancing. And what I mean by that is a lot of times you'll have maybe one element on the left-hand side and the right-hand side, and they're only in one thing on each side. So they're kind of like only in one thing on each side. That's something that's probably fairly easy to balance up and do that. You probably want to save situations where you have like an element on each side, but that element's in multiple things on each side. So if they're on multiple things on each side, there's a lot more going on with that, and kind of saving to the end. You want to continue to put coefficients until, frankly, you have the same number of elements on each side, and then you should have the balanced equation. Now, when you balance an equation, there's really two things that you need to make sure of to have what is considered a properly balanced equation. And that is, when you're all said and done, all the coefficients need to be whole numbers. So all the coefficients that you put in front, they all need to be whole numbers. And they also need to be the simplest set of whole numbers. So what do I mean by that? I mean, like, if we take this equation and we'll just assume it is balanced with those coefficients, although this equation just be balanced, I could do what with all those coefficients? I could reduce them all down by 2. Yeah, I could divide them all by 2. So you would want to do that and go across and give you the properly balanced equation, which would be this in this case. And that does happen because sometimes people could see larger numbers to balance it, and it will still be balanced. You'll still have the same numbers of everybody on each side, but there'll just be larger numbers. So if you find yourself at the end when you balance the equation, you look at all the coefficients, and you could divide everybody by a common number to reduce them down and still have a whole number for everybody, you should do that to have the properly balanced equation. Any questions on that? All right. So let's take a look at one here together, and I'll explain sort of my way of going at it here. So let me just rewrite it here. NO plus H2, a little N2 plus H2O. All right, so we're going to balance this guy. I personally think it's sometimes very helpful for people to make like a little table as you're balancing. So what I would do is obviously there's the reactant side, there's the product side, and obviously we have three elements: nitrogen, oxygen, and hydrogen in this case. So all I'm just going to do to start with is just kind of count up what I got going on each side of the arrow. So on the left-hand side, I got one nitrogen right there. On the right-hand side, I have two nitrogens. Remember, this number always goes to the guy to the left. So I got two. For oxygen, I have one there on the left. And on the right, I also have one right there. And lastly, for hydrogen, I have two on the left and two on the right. So what this table does is it sometimes allows you just to kind of focus in on what might you want to start with. Now, clearly in this case, everything is balanced, right? Except for our nitrogen. So I would say in this case, nitrogen would be a pretty good place to start. I have one nitrogen on the left. I got two on the right. Once again, we can only balance it with a coefficient. So we're going to put a 2 in front of the nitrogen on the left. Remember that this 2 now gets distributed to both of the guys behind it. So this will now give me two nitrogens. That will also give me 2 times 1 for the oxygen, which will give me 2. Hydrogen is still 2. This is very common when you balance an equation. You fix something and frankly screw up something else. It's very, very common. So our table here still helps us sort of think about where we might want to go next. Obviously, at this point, we fixed the nitrogen but messed up the oxygen. So that makes sense to go to oxygen now to try to balance it. And we can see we need to balance it on the right-hand side. We got 2 on the left, 1 on the right. So again, only a coefficient going to go in front here of the 2. We're going to put a 2 in front of the H2O. Once again, that is going to count for both of the guys behind it. And that will give me 2 nitrogens on the right. 2 times 2 is 4 hydrogens on the right. And 2 times 1 for the oxygen will give me 2 for the oxygen there. Questions on that one there? I'm close now, right? The only thing left to balance is, yes. What's that? Why did I put the 2 on the H? I put the 2 on the H because that's where the oxygen is, right? Are we talking about here? Yeah, so that is where the oxygen is. So we need to put the coefficient in front of it. And we cannot put the number in between anybody. So it's got to go in front. So it also will go for the hydrogen as well. Yeah, so anybody behind it. We did at that point. So before I put the 2, we had basically this. We had 1 oxygen and 2 on the left. So we needed the 2 on the right. That's good. Yeah. 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 We're not done balancing, if that's your question. So we do need to go back to the other side here to finish it. But up at that point where I put the 2 here, it really only affected this guy. This guy is still 2 at this point. Now we do have 4 hydrogens because I had to put a 2 over here. So now I need to go back to the left-hand side now and fix it, right? Because it's not balanced at this point. We are short some hydrogens on the left. So our table shows us that we are not completely balanced at this point. We are now unbalanced right here at our hydrogen. And that now is a very easy fix because we could go back to the left and put a 2 in front of that hydrogen. And that now will give us still the 2 times 1 for the nitrogen, the 2 times 1 for the oxygen. And now we have our 2 times 2, which is 4. And now we are balanced on both sides of the equation. Any questions on that? Yeah. So the ultimate goal is to end up with the exact same number of each element on each side of the equation. So it is sort of dependent on sort of where you start as to, what you need to add or what number you need to be. It won't always obviously be a two, which just happens to be in this case twos that we need to add. It's based on really what you had there. So originally, everything was balanced in this equation originally, except for the nitrogen. So that's why we started with the nitrogen on the left, and we had one on the left to start with and two on the right. So that's why we had to put that first two over there on the nitrogen. By putting that two on the nitrogen, it actually screwed up the oxygen part. So that is what we had to go fix next. And that's why we had to put the two in front of the water on the right, because that's the only place oxygen is on the right. And that messed up as we saw hydrogen, which is very common. Then we had to come back to the left there and fix this equation. A lot of like you fix one thing, but you mess something else up and you kind of have to go back and forth. Sometimes each side, sometimes you do like one side at a time, kind of go back and forth. Sometimes you might even have to do kind of both sides at once to start it and start to balance it. Yeah, so like for example here, obviously when we made our table, clearly everything was balanced except for nitrogen. So it makes more sense obviously to start with the nitrogen. And as you fix the nitrogen, it's going to mess something else. And always when you balance something, in most cases, if you put a coefficient in front of somebody, you're going to mess somebody else up. And that's where the table is sometimes very helpful because it kind of visually you can see, kind of where you maybe should go next. There will be some, and we'll see some in just a second, that you may have, for example, in this case, we really only had each element in one thing on each side. They weren't in multiple things. We didn't have like an oxygen and two different things. So sometimes when you have like one element on one side that's two different things and one thing on the other side, you oftentimes want to save that guy for the end because it's just easier to kind of fix it at the end. Or something like that, or even when balancing an equation, you do not have to put a one. You're talking right here, correct? It's assumed that if there is nothing written there, it's a one. And when you balance equation, you could just leave it blank. Just remember that when you do anything like that, it is a one. And that's the same thing for, excuse me, for example, when we look at the formula of water with nothing written there, it's assumed to be a one. And again, most of the time in chemistry, we don't kind of like write the one. So if you don't see anything there, it's assumed to be a one. And that's why, for example, when I put the two in front of it to fix the oxygen, we're basically doing 2 times 1, and that's how we get to the 2, basically, that's there. And it's because really, if you draw water, that 2 means that you don't have one of these, but you have 2 of these. And that means if you look at it, right, you have 2 oxygens, right? And there's your 4 hydrogens that you get by doing that. So that's basically what it means. When you put those coefficients, that's basically how many of the thing. Other questions? All right, let's try a few here. Make sure. All right, so why don't you give this one a go, balance this one up, see what you come up with this here. So I'm going to make my table here, and we got carbon, hydrogen, and oxygen. And here on the right hand or left hand side, we have 3. Again, this goes to the guy to the left. And over here, 1. We have hydrogen, 8, and 2 over here, and 2 oxygens and the left hand side. Now on the right hand side, we have 2 oxygens there and 1 more there, which makes 3. So we don't want to miss anything there. All right. So in this case, once again, to sort of answer a question that we were talking about, here we have really nothing balanced in this particular case. So the easiest thing to fix is, for example, carbon is a good place to start because when we look at carbon, it's in one spot on each side, right? Basically, it's only in one thing. So we can very easily fix the carbon. Here, I might not want to, for example, start with the oxygen, and that is because when I look at oxygen, it's there, but oxygen on this side's in a couple different places. So to me, I would probably leave that towards the end and kind of work on everything else that's a little bit easier to fix. So we can fix the carbon very easily by putting, again, a 3 in front of it. And that is, again, going to go to everybody behind it, which will be 3 for our carbon. We still have 2 for our hydrogen. And now we do have 3 times 2 here, which is 6. And we do have 1 more oxygen over here. So that's going to give us a grand total of 7 for our oxygen. Any questions on that there? Now, at this point, I am personally going to still avoid the oxygen because it's still in a lot of places. Much easier to balance at this point is hydrogen, as it's again only in one thing on each side, right? So we have 8 on the left of hydrogen. To fix the hydrogen on the right, we will need to put a 4 in front of it. Now, we didn't do anything on the left, but the right-hand side here still has 3 carbons. Hydrogen now has 4 times 2, which is 8. And now in terms of oxygen, we still have 3 times 2, which is 6. But now we have 4 times 1, which is 4. And that now becomes 10 when we add it together. This is why we want to really kind of save the oxygen for the end, because if we try to balance the oxygen in front, that's going to make it really hard to get the hydrogen and carbon balance, because every time we play with the oxygen, we're going to change the hydrogen and carbon. So again, we want to kind of leave it for the end. The reason we want to leave it for the end now is it should be quite easy to balance, right? Because all we have to do now is go to the left-hand side and fix our oxygen. And we could fix our oxygen by putting a 5 here. And nothing changed here. So I still got 3 carbons, still got 8 hydrogens, and 5 times 2 is 10 oxygens in this case. And now with all my scribble on there, we do have a balanced equation there in terms of our coefficients. So this is really what I was talking about earlier, where again, if you have a situation where you have an element and one thing on one side, but in multiple things on the other side, it's usually a great idea to just kind of leave it for the end. Any questions on that? All right, let's try a few more here. Make sure. All right, why don't you balance up this equation, see what you come up with. All right, let's take a look here. We're going to make a table here, reactant side, product side. We'll do our elements, BOH. On the left-hand side, we have 2 borons. That'll be a 2. Right-hand side, we have 1. Left-hand side, in terms of oxygen, we have 3 here. And again, we have 1 more over there, which makes 4. On the right-hand side here, this 3 in parentheses does get distributed to both of the guys that are inside the parentheses. So we will have 3 oxygens there. Left-hand side, we have 2 hydrogens. And right-hand side, again, distributing that 3 in gives us 3. Once again here, we got really nothing balanced. There's not a lot to work with on the right-hand side, so might as well just start on the right-hand side. And because we got 2 borons on the left and 1 on the right, it's very easy to fix that. We can put a 2 in front of it. When I put that 2 in front of it, it does get distributed to everybody. So it goes to this guy, it goes to this guy, and it goes to that guy as well. So it goes to everybody behind it. That means that when we are sort of adding up what's going on the right-hand side here, we do have to do a couple of math things here. So we definitely have 2 times 1 is 2 for our boron. We now have, however you want to do it, we have 3 times 1, which is 3 for the oxygen. And then we need to multiply it by 2. So 3 times 2 is 6 there. Same thing for the hydrogen. 3 times 1 is 3. And that 2 in front also gets multiplied, which would give us 6 hydrogens. So if you do have parentheses and a subscript small number, you got to multiply it to everybody in there. If you put a coefficient in front of parentheses, then you also got to multiply that as well. Any questions on that there? I chose 2 because originally on the left-hand side we had 2 boron and we had 1 on the right. So that is, boron is basically just 1 by itself. So it's very simple. We could balance it, even though it's attached to everything else. There's just 1 boron there. So it's just simply to put it 2. Yeah. Other questions? All right. Clearly at this point, we don't want to play with anything on the right because that's going to screw up all the numbers. So we definitely want to go to the left here to fix things. So what we need to fix at this point is actually the oxygen, the hydrogen. Once again here, when I look on the left-hand side at oxygen, it's in how many things? 2. Hydrogen's in how many things on the left? Just 1. I'm going with hydrogen here because it's just on 1 thing. It won't mess up too much stuff here first. So I'm going to fix the hydrogens first for that reason. I got 6 hydrogens on the right. I only have 2 on the left. I can again easily fix the hydrogen by putting a 3 in front of it. That's going to give me on the left here 2 borons still. Now in terms of oxygen, I have 3 here. And I do get to multiply this to both guys, which means I also have 3 oxygens there. And this oftentimes happens as well. I actually fix my oxygen by fixing my hydrogen. So it did both. It did double duty there. And for my hydrogen here, 3 times 2 is 6. Yeah. So again, that also sometimes happens. Sometimes what you'll find as you're balancing equations is everything will just sort of fall into place as you kind of put some coefficients in there. Even things you weren't trying to balance will sort of fall into place in terms of being balanced. Any questions on that one there? On the left or the right? The left. I got 6 for the oxygen because if we look at the first one, there's basically 3 oxygen here. And then we have this coefficient here, which is a 3, which also goes to the oxygen, which would give us another 3. Yeah. Other questions? And obviously that 3 goes to the hydrogen as well. Yeah. Other questions? Yeah. Yeah, the whole goal here is to end up, like I said, like we did here. This is why the table is sometimes helpful because frankly, I can see now that as long as you added everything correctly, it should be balanced. We have the exact same number of elements on each side of the arrow. That is the ultimate goal of balancing, is to get the exact same numbers on each side. Again, because ultimately the reason is we don't ever lose any elements. We don't change elements in a chemical reaction. All we're doing is breaking bonds. So in this case, for example, when we start with 2 borons, we should end with 2. And we start with 6 oxygens, we should end with 6 and so forth. Other questions? All right, let's try another one here. See. Give this one a go. Balance it up. Okay, so let's take a look, see how you're doing on this one here. So we'll start the same way. We'll make a little table that might be helpful. Maybe not, we'll see. All right, so on left-hand side, nitrogen, we got 1. Right-hand side, we got 1. That's not too bad. Left-hand side, hydrogen, we got 3. Right-hand side, we got 2. Left-hand side, oxygen, we have 2. Left-hand side there we have 2. Right-hand side we have 1 there, and again 1 more there, which would make 2. So it appears not too bad. It's everything's balanced except for obviously in this case our hydrogen. So that is, I think, where we should start. Now in this particular case, we have 3 on the left-hand side and 2 on the right-hand side. So common number between 3 and 2 is 6, right? If you multiply them together. So we basically want to make 6 on both sides. In this case, we're actually going to put a coefficient on both sides to start with. So to get my hydrogen to 6 on the left-hand side, I need to put a 2. Get my hydrogen to 6 on the right-hand side, I do need to put a 3 there. So that gives us on the left-hand side now 2 nitrogen, as this guy goes for everybody. That gives us now 6 hydrogens, and we still have the 2 oxygens. Right-hand side here, we got still the 1 nitrogen. Hydrogen, we have 3 times 2, which is 6. And now for oxygen, we have 1 there. And we also have 3 times 1, which is 3. So that's a 3 and a 1, which will give us 4. So we successfully fixed the hydrogen, but royally messed up the rest of the equation there. No problem. if you had to guess where I'm going to go next, am I going to go nitrogen or oxygen? Which one am I going to go next? I'm going to go nitrogen again. It's in one thing on each side, so it's the simplest thing to fix, right? So might as well save the headache for the end. So to fix the nitrogen, we got 2 on the left, 1 on the right. So we're going to put a 2 here on the right-hand side. That's going to give me 2 nitrogens. We still have our 6 hydrogens from there. And now in terms of oxygen, I have 2 times 1, which is 2. And I still have the 3 times 1 on this side, which is 3. So 3 and 2 now is 5 at this point. Any questions on that so far? What's that? Yeah, because the reason we want to start on the hydrogen is because it was the only thing that was not balanced. Everybody else was balanced. So you might as well start first with whatever is not balanced and probably start with whatever is not balanced that is probably easiest to fix by putting a coefficient. Yeah. Yeah, I think the last one, maybe everything was uneven, so you could have started, anywhere. But even in that one that we just did on the last one, we really wanted to start with the boron because that was still the easiest one to fix in that case. Yeah. Other questions? All right. So clearly we don't want to change any numbers because we're going to be here all day. And now we need to somehow, turn a 5 into a 2, or we could just go to the next problem and leave this one. That's a good idea as well. It seems like the best move. All right. So we basically need to get a 5 there on the left-hand side. So we want to do perhaps something that we can multiply that by to get us a 5. Perhaps we could do something like 5 divided by 2. And if I put that there, like a little fraction action, that's going to give me 2 nitrogens. That will give me 6 hydrogens. And when I take 5 halves times 2, those cancel and I end up with 5. Here's the deal, right? We needed a 5 on the left, right? So I just laid up a fraction, which clearly it actually did balance the equation, yes? Equation is balanced. Is that equation properly balanced? It is not, because when you balance an equation, all the coefficients need to be what type of numbers? Whole numbers. So this is a good illustration that sometimes you may actually need to use a fraction to balance the equation to get the right number that you need, because there's no way to turn a 2, right? There's nothing you can multiply besides what we just did, perhaps, a whole number by 2 and get a 5, right? There's no way to do that, basically, right? So the only way that we could actually get a 5 on that side is to use a fraction. Now, we could absolutely use a fraction to balance the equation. The only thing that we cannot do is leave the fraction. So although we could use it to balance it, we do have to get rid of it. So to get rid of the fraction, you need to multiply by the denominator, right? That's the guy on the bottom. So here we need to multiply not just the fraction by the denominator, but we actually need to multiply the entire equation by the denominator. And if I do that, I will end up with 4NH3 plus, again, 5 halves times 2 is 5O2, 4NO plus 6H2O. And if I did not screw anything up there in my multiplying, I will now have a balanced equation that has all whole numbers for the coefficients. Let's double check. We have now 4 nitrogens on the left. 4 times 3 is 12 hydrogens. 5 times 2 is 10 oxygens. On the right-hand side, we have 4 nitrogens. 6 times 2 is 12 hydrogens, and 4 oxygens there, and 6 oxygens there is 10. So this equation is properly balanced. And this very often happens when you have an equation like this, where you have like a diatomic molecule, one of those elements that's diatomic, like the O2, and you have that same element and 2 things on the other side. So very commonly, that is a situation where you might have to pull out the fraction. So you may say to yourself, how do I know what fraction to use? The answer is it's a really simple sort of formula to figure out what fraction you need to use. So I'm just going to back up here. I'm going to take my fraction out. And before I did my fraction, I'll get rid of all this here. clean it up a little bit here. All right, so before I actually did my fraction, right, we're going to recalculate what we got going on each side. So again, going back to this top equation, on the right-hand side, we have 2 nitrogens, we have 6 hydrogens, and we had 2 oxygens there and 3 there, which made 5 oxygens on the right-hand side. On the left-hand side, we had 2 nitrogens, we had 2 times 3, which is 6 hydrogens, and 2 oxygens. So that's what we were looking at before I laid it up, right? So everything is balanced. The nitrogen's good, right, at this point. The hydrogen is good at this point. Just the oxygen is bad. The only place it does not go to the those numbers, because that's just going to put you in a bad circle that you're never going to get out of, right? So I have to do something with the O2 because that's the only place that does not have a coefficient. So as I mentioned before, we have 2 oxygens on the left. There is no whole number that, again, you could multiply a 2 by and get a 5. Everybody agrees? Yes. I know. I went back to before I did this. So we're before this stuff. So I'm back here where we're trying to figure out how to balance this equation before I use the fraction. Just to make sure everybody understands how we use the fraction and how to choose the fraction here. So before we did that, we have 5 oxygens on the right, 2 on the left. Once again, there is no whole number you can multiply by 2 to get a 5. So that should tell you, again, you got to go with a fraction. So here is what you need to do to pick the proper fraction. The number that goes on top, which I believe they call a numerator, I think, is the number that you need. Yeah. So the fraction part that you're going to choose, the number on top should be the number you need to balance the equation, which in our case is which number? 5. So that's why I chose 5. The bottom number for the fraction should always match the diatomic subscript. What is the subscript on O2? That's what it needs to match. Yeah. That way you will always pick the right fraction. Number on top, the number you need. Number on the bottom matches the subscript that's there. And you'll have the right fraction. Once again, now that we have the right fraction, when we take 5 halves that we put in as our coefficient, that's why we're going to multiply it by 2, which is why these numbers need to match so that they will cancel out when you multiply them. And you'll be left with the top number, which is the number that you need. Yeah. Question on that. And obviously at this point, we cannot leave that fraction. So we have to multiply everybody by the denominator so that we get whole numbers at the bottom. So at this point, we could then once again multiply by 2. And that will take us back here to this equation that I probably shouldn't have scratched out, which is the properly balanced equation. Make it fix it. There it is. We'll get that equation down there. Question on that. So again, very commonly, if you find yourself at that point where you're like, I just got to somehow turn that into a number that I can't multiply a number by, probably a fraction is what you should probably look at. Again, top number you need, bottom number should match the subscript that's there. Do you have a question?
Everything by 2 and
Yep. Yeah, you multiply all the coefficients by 2. So we have to clear the fraction, and the only way to clear the fraction is to multiply by the denominator, the number on the bottom. So in this case, we would multiply by 2. And we would take this 2 and multiply it by this 2, which is how we get to the 4. We would take this 2 and multiply it by the 5 halves, which is how we get the 5. Take the 2, multiply by that 2, we get a 4. Take the 2, multiply by that, we get a 6. And that will clear the fraction and now give you an equation on the bottom that has all whole numbers, and it will still be balanced, which is your goal, right? To keep it still balanced. Other questions on that there? All right, so let's take a look at a couple other balancing equation situations that might develop here. Actually, let's take a 5-minute break. Come on back in. Let that soak in for a second. Don't be too long. Come on back. Okay, we're going to continue on here. So let's talk a little bit about a few things that sometimes develops as you're balancing equations, and some of the things that you could do to make it a little bit easier on yourself. So let's just say we have this equation here, and this equation here has a couple of things in there that will make it perhaps a little bit more difficult to balance if you kind of take the same approach that we were doing earlier, which is take basically element by element sort of approach. So when we look at this, we actually have some polyatomic ions that are present here. So for example, we have phosphate on the left. We also have phosphate on the right. We have sulfate on the left, and we also have sulfate on the right. Now, I would say that whenever you perhaps have an equation to balance that there are polyatomic ions, the same polyatomic ion on both sides of the arrow, a lot of times it's a lot easier to keep those guys together and sort of balance them as whole units rather than going element by element. You could definitely still go element by element, but as you can see, there's some parentheses, there's a lot of multiplying in and multiplying out, and there might be a greater chance for error. So if you can see some polyatomic ions that are the same on both sides of the arrow, I would keep them together, and that is actually where I would start balancing. I wouldn't necessarily even make a table necessary at this point, and I would just sort of balance it that way. So what do I mean? So if I look, for example, in this case, on the left-hand side, how many phosphates do I have? I have 2, right? And on the right-hand side, phosphates, I have just 1, right? On the left-hand side here, I have 1 sulfate, right? And on the right-hand side, I have 1 sulfate. So in terms of sulfate, it's actually balanced. They're good, right? We got 1 on each side. Probably don't want to play with that just yet. So here where I would start is with the phosphate, and just keep it really simple. I have 2 phosphates on the left. I have only 1 on the right. So to fix the phosphate on the right-hand side, I should put a 2 in front of it, right? Now to put a 2 in front of the phosphate, I got to put the 2 obviously in front here, in front of the silver. When I do that, that is going to give me the 2 phosphates that I need to balance it, correct? Now, when I do this, I did not just fix the phosphate here, but I also did something to my silver, correct? Because it was in the same compound. That is what's going to tell me where I should go next. So I fixed the phosphate. The phosphate has the silver attached to it. And now with the silver, how many silvers do I have by putting that 2 there? I have 6 on the right. Now, when I look at the silver on the left, how many do I have? 2. That's where I'm going next. So I'm going to go over there and fix the silver now, right? To fix the silver on the left-hand side, what do I need to put in front of it? 3. This now fixes the silver with 6, right? But that also now affects the sulfate. How many sulfate units do I have now? That is where I'm going to go next, right? So I'm going to go to the right-hand side. How many sulfates do I have? On the right-hand side, 1. So to fix that, I need to put a 3 in front of it, right? That will give me 3 sulfates. That then also affected iron. How many irons do I have? And now how many irons do I have on the left-hand side? That worked out nicely. I'm done. Yes. So by keeping those together, it is a lot simpler to balance them as whole units. You start with a polyatomic ion, and then whatever you put the coefficient on there, that's with the polyatomic ion, that's where you go next. And you just kind of keep going to the next guy. Any questions on that move there? Yeah. And again, you could definitely still go element by element, but there's a lot more kind of multiplying in and multiplying out. Why don't you try a couple here? Why don't you balance this equation? Write the coefficients because that kind of defeats the purpose, I imagine. There you go. Let me do that. Why don't you also maybe do this one here? Even though they look really scary. and one non-polyatomic ion for fun. I don't know how fun it'll be, but we'll try it here. All right, why don't you try balancing these equations and see what you come up with, huh? These here, again, I do see a polyatomic ion, at least one in the first one there, and it is on the same opposite sides, the same form of it. So at least I got one polyatomic ion, so I'm going to start with that. Again, I'm going to keep the polyatomic ion together, and that is where I'm going to start my balancing. So I have how many nitrates on the left? 2. And nitrates on the right, I have 1. So to fix the nitrate on the right, I need to put a 2 in front of it. That gives me the 2 nitrates that I need. Now, it also affects the other thing that's with nitrate, which is potassium in this case, right? That now gives me how many potassiums on the right? And that again is where I'm going to go next to fix, right? So I now have 2 potassiums on the right. I have how many potassiums on the left? So I'm going to fix that by putting a 2 in front of it, right? That gives me 2 potassiums. Now I'm going to look at the chlorine, right? Because it's attached there. That gives me 2 chlorines on the left. How many chlorines do I have on the right? I'm good, right? How many leads do I have? PB on the left. And on the right, I'm balanced, yes. So again, much simpler when you have those polyatomic ions, at least one in there. I would start with those, keep them together. Once again, if you do want to go element by element, you can, but there is going to be a lot more sort of multiplying in up when you have those polyatomic ions involved. Where do you go next to fix? And you just kind of keep following. This is typically what will happen. Eventually, everything will kind of fall into place in terms of the balancing part of it. Now we look at the second one. I got the same deal. I got sulfate here and sulfate here. I also have nitrate here and nitrate here. So in this case, I actually have 2 polyatomic ions to choose from. You could choose either one to start with. One might work out better and one might not work out so good. So I'm going to show you the one that doesn't work out so good and show you it's not a big deal if it doesn't work out good for you. So I'm going to start with the nitrate here. And on the left-hand side, I have how many nitrates? 3, right? So to fix the nitrate on the right-hand side, I'm going to put a 3 there, right? How many copper? 3. On the left-hand side, how many coppers do I have? That's a problem, yes? That's like not, you can't really make that 3 into 2 without going crazy. So maybe that was not the best one to start with. So all you have to do is, scratch it out, grab an eraser, it's not a big deal. I'm going to start now with the other polyatomic ion and see if that works out a little bit easier. So now we're going to switch it up and go to the sulfate first. So I have 1 sulfate on the left. I have how many sulfates on the right? So now I want to fix the sulfate on the left by putting a 3, right? That now gives me 3 sulfates. How many carbons? I can see that. Whatever that thing is. How many coppers that is? That is 6. On the right-hand side, how many coppers do I have? Only 1. So to fix that, I put a 6. Yeah. So that is 6 coppers. I'll get it right. And that now gives me how many nitrates? 6. How many nitrates do I have on the left? 3. So to fix the nitrate, I need to put a, that gives me how many aluminums? How many aluminums do I have on the right? Now I'm balanced. That one worked a lot better, right? So it's not a big deal. We could just switch it up. By the way, we originally had a 3 on the copper on the left, right? Or on the right. And then we had a 2 on the left. You could find the common number. 3 times 2 is 6, right? That's what we ended up getting copper to basically over here. You could fix it that way by doing it that way if you wanted to as well. So hopefully you can see with these polyatomic ions, it's much quicker, much easier just to keep and just some. And like in that situation, like I showed you there, even if you pick the wrong sort of polyatomic ion to try to balance, I would erase it and try the other one, and the other one probably will work a lot easier, like obviously it did here. Any questions on any of those 2?
How do you know which one's the polyatomic ion?
It's like what we talked with in nomenclature, that list of like nitrate, sulfate, that table and stuff that we talked about. Those are the polyatomic ions. You do need to know the ones that are in that chapter in that table and stuff like that. Yeah. So I believe that was chapter 6. Yeah. Other questions? But usually you can see them in an equation. They're pretty obvious in a lot of sense because a lot of times they'll have parentheses. Because remember, you have to put parentheses around polyatomic ion. If you have times you'll see that sort of in the equation. They'll be like the guys in the parentheses and they're groups of nonmetals together, so they'll be sort of recognizable. Let's take a look at the bottom one here, and I think I'll rewrite it on this page. I feel like I'm gonna need more room. All right, so C4H10 plus O2, CO2 plus a little bit of water, a little combustion reaction happening. So here we do not have polyatomic ions, so we're going to roll with maybe our table. So we'll go back to our table approach here. So we got carbon, hydrogen, and oxygen. So here we do have 4 carbons on the left, 1 on the right, 10 hydrogens on the left, 2 on the right, 2 oxygens on the left. Once again, here we have 2 oxygens there, plus 1 more there, makes 3. So clearly here, if you had to choose, which one would you go with to start? Carbon seems like a good one. That is carbon, not copper, I suppose. So carbon seems like a good one to go with here. So we're going to do carbon, which is pretty easy. It's by itself. We could fix it by putting a 4 there, right? And when we put a 4 there, that's going to give us 4 carbons. We will still have 2 hydrogens. Now, when we look at the oxygen, we're going to have 8 for the first guy, and we still have 1 more over here, which gives us 9. Yeah. Clearly, at this point, we have hydrogen and oxygen to choose from. Here, hydrogen would still be the easiest to fix, as oxygen's in a couple of things there on the right and 1 thing on the left. So I'm going to fix the hydrogen, which is in 1 thing on each side. I need to put a 5 right about there. That's going to give me still 4 carbons. 5 times 2 is 10 hydrogens. Now, in terms of the oxygen, we still have 8 there, but now we have 5 times 1, which is 5. So 5 and 8 is like a 13, dare I say. Yeah, that's a 13 happening there. We have now put basic coefficients on the right-hand side, which we do not want to play with. The only oxygen on the left is the O2, and I need to make my 2 into a 13. What should I use here? A fraction, yes? So we know the very simple formula of the fraction I should choose. The number that goes on top is the number we need, right? So what number do we need? 13. I'm going to put lucky number 13 up there. The number on the bottom should match this number, right? Which is a 2. And there we go. Let's see how we did. We now have 4 carbons, 10 hydrogens, and again, when we take 13 over 2 times 2, these guys cancel and we end up with 13. We are technically balanced at this point, but it is a properly balanced equation. It is not, because we still have the fraction. So once again, to get rid of the fraction, we need to multiply this entire equation by 2 in this case, which is the denominator here in our fraction, so that we will clear it. That will give us 2C4H10 plus 13O2 gives us 8 CO2 plus 10 waters. And again, if we did not mess anything up, we should definitely still be balanced. So we have 8 carbons on the left, 8 on the right. 2 times 10 is 20 hydrogens. 10 times 2 is 20 on the right. 13 times 2 is a lot, but 26, I think. Over here, we have 16 oxygens, and 10 times 1 is 10. 10 and 16 is 26, yeah. And we are balanced in this case. Question on that there. Now, if you could see the larger numbers, whole numbers, you could do that. You don't have to use the fraction. Again, sometimes people could see larger numbers that will work, and you can maybe reduce it down. It's all good. It doesn't really matter how you get there. As long as you get there, to it being balanced on both sides, all whole number coefficients, and the simplest set of whole numbers. Question on balancing there. Yeah. All right. All right, now that we know how to balance equations, let's talk about types of reactions and ways to classify reactions. So really the deal is here, there is really three reasons, as we will see, why a reaction takes place, basically. You could almost boil it down to these three reasons as to why that particular reaction actually took place. One reason is the making of a solid, which is sometimes referred to as a precipitate, sometimes abbreviated PPT. The making of water, little H2O. And lastly, a transfer of electrons. Pretty much every equation or reaction that you come across will pretty much boil down to one of those three things happening. And that's really the reason why a reaction takes place. And also the reason why reactions don't take place is none of those things might happen, so nothing's going to happen. When we talk about classifying reaction, there's really two big classifications of reactions. There are what are referred to as redox reactions. And redox reactions take care of the transfer of electrons part of the program. So basically, that is ultimately what's happening in a redox reaction. That is like a big classification to which more specific classifications of reactions can be described. The other big type of reaction or classification is what known as a double displacement reaction. And in a double displacement reaction, it is responsible for making a solid and making water. Also, under like the double displacement umbrella, there are more specific ways you could classify a reaction. As we will see, that you can look at a reaction, you could actually classify it like three different ways, the same reaction. So there are multiple ways you could classify the same reaction. So let's start with redox reactions and sort of what that means. So oxidation reduction reactions are redox reactions, and redox is the shorthand for oxidation reduction. And what does that mean? It means essentially if something is going through oxidation, one of the definitions is it will lose electrons. And if something goes through what is known as reduction, it will gain electrons. They always happen together. So if somebody is going through oxidation and losing electrons, somebody else is going to go, thank you very much, and pick up the electrons, and they're going to gain the electrons. Sometimes people remember this as Leo the lion goes grr. Loss of electrons, oxidation, gaining of electrons, reduction. Other people are fond of the oil rig. Oxidizing is losing, reducing is gaining. You could put Leo the lion on the oil rig and he goes grr, and you don't have to choose. You could just use all four of them together if you like. But what does this really mean? This really means when you look at what is known as the oxidation state, or like the charge on something, as the charge goes from the left-hand side of the arrow to the right-hand side of the arrow, the oxidation state or the charge will change. So how do we know if something's really being oxidized or reduced? Well, hopefully we know that when somebody loses electrons, do they become positive or negative? They do become positive. And when somebody gains electrons, they become negative. So really the simplest way to figure out did something go through oxidation or reduction is my old classic friend, the number line. I believe on a number line there's a 0, and to the right of the 0 is positive numbers, right? And to the left of 0 are negative numbers. So if something loses electrons and gets oxidized, it becomes more positive. So if you look at the charge of whatever you're looking at on the left-hand side of the arrow to the right-hand side of the arrow, and you see the charge move in this direction, becoming more positive, that means that that thing went through oxidation. When somebody gets reduced, they gain electrons, which means they become more negative. So what you'll see in the charges as they go from the left-hand side to the right-hand side, they will become more negative and move in this direction, in the negative direction, and that thing will be going through reduction. So what do I mean by that? Well, if I had, for example, sodium metal that has no charge, by the way, anything that is just an element by itself, not combined with anything, has no charge. And let's just say it goes to the other side and becomes sodium with a charge, which is a +1, yeah? My sodium started at 0, right? If I whip out my number line. My sodium started at 0 and ended on the right-hand side at +1, which means it's moving in this direction, right? And when I move in that direction, what happened to the sodium? Did it get oxidized or reduced? It got oxidized. This got oxidized, right? If I look at my Cl2, which is chlorine, and I got like a couple of these guys over here. My chlorine over here on the left has no charge, right, by itself. On the right-hand side, this chlorine, which is chloride, has what type of charge? -1, right, basically. Again, if I look at what's happening with chlorine in this case, it started at 0 and ended at -1, which means it's moving in that direction, becoming more negative. That means in this case, the chlorine became reduced, right? And this guy got oxidized. So if you can figure out sort of, it's really the oxidation state, but we'll call it charges. You figure out the charges of everybody on each side or whatever you're comparing, you basically just move along the number line. So if you move more negative, it got reduced. If you move more positive, it got oxidized. For example, you could even do it with two things that have positive charges, like this guy. So let's say I had iron with a +2 charge, and it goes to iron with a +3 charge. What happened to the iron? Did it get oxidized or reduced? Yeah, so again here, if we start at +2, which would be like here, it ended at +3, which is moving in that direction, becoming more oxidized. There it is. Any questions on how to work that there? Yeah. All right. So here, if we look at the formation of sodium chloride here, which is sodium metal plus some chlorine gas, makes some sodium chloride. Let's think about what's happening here. So that is no charge because it's just by itself. Again, they have to come together to get a charge. Chlorine also, naturally, the way it comes, has no charge. But when sodium and chlorine come together, that's an ionic compound, right? And that's made up of ions. And the sodium is +1, right? And the chlorine here is -1, right? So again, as we saw on our number line a second ago, if we look at the sodium on the left-hand side, 0, sodium on the right-hand side, +1, it is the sodium here, again, that is being oxidized. You want to know the good thing about oxidation reduction? If you could figure out one of the guys, whatever's being oxidized or whatever is being reduced, by default, the other thing has to be doing the opposite thing because it always happens together. So if you could just figure out for sure, I know this is being reduced, by default, the other guy's got to be oxidized. Or if you know for sure this guy is being oxidized, the other one has to be reduced. So you actually don't have to figure out both. You actually just need to figure out one, and the other one will be the opposite thing happen. Again, we could do like we did on the other page there. Chlorine started at 0, ending at -1, becoming more negative and being reduced in this case and oxidized. This is basically what's happening here is the sodium is transferring electrons over to the chlorine. That is how sodium, as we talked about in bonding, becomes a positive charge. It lost its electrons. That's how chlorine becomes a negative charge because it picks up those electrons. This is a redox reaction, is the big classification of this, a transfer of electrons that's happening in this case. Same thing here. If we look at magnesium and oxygen, magnesium by itself is 0. Oxygen by itself, O2, is 0. When magnesium and oxygen come together, magnesium has a charge. What is magnesium's charge? +2. Oxygen is group 6, which is -2. So again, if we look at our number line in this case, magnesium is starting at 0 and ending at +2, right? That means magnesium is doing what? Yeah, it's being oxidized, right? Oxygen by default is being reduced, but we can still figure it out. Oxygen started at 0 and ended at -2, heading in that direction, right? And it is being reduced in that case, becoming more negative. Also a redox reaction. This classification, really big classification of it, is a redox reaction. Same thing's happening here. This guy is sending electrons over there. Whenever you have a metal and a non-metal together, which one should always lose electrons? The metal, right? For all those periodic trends. So whenever you have an ionic compound that's formed and you have a metal and a non-metal, the metal should always be the one being oxidized. The non-metal should always be the one being reduced, because that's what happens. They become positive, the metal, non-metal becomes negative, means the metal always loses the electron, always is oxidized. The non-metal always gains electrons, becomes negative, is always reduced. So that's always the case when you have a metal non-metals. Very quickly you can determine what's being oxidized and reduced. By the way, when we talk about what's being oxidized and reduced, it's always the guys on the left-hand side of the arrow, the reactants, or what's happening there. Those are what we're talking about as being oxidized and reduced. Now, you can also look at oxidation and reduction looking at oxygen and hydrogen, which we will see later on when we talk more about organic chemistry, because organic chemistry deals with a lot of non-metals. So there's not a lot of metals and oxidation states that you can maybe look at. So there are a couple other definitions of oxidation. Oxidation, in addition to losing electrons, means losing electrons there. It also can mean that it has gained oxygen as you go from reactants to products. It also can mean that it has lost hydrogen as you go from reactants to products. So those are 3 definitions of oxidation. Reduction has similar definitions. It means, as we talked about, gaining electrons. It also means that it has lost oxygen as you go from reactants to products, and it has gained hydrogen as you go from reactants to products. I would say we probably won't see too much of these definitions until we get to organic chemistry, and then we will see a lot of that definition. Here in sort of general chemistry, we oftentimes look at electrons being gained and lost, but we definitely will see those definitions as we get into organic chemistry a little bit later on. So what does that mean? If I look over here, the sulfur over here has how many oxygens? And the sulfur over here has how many oxygens? It gained oxygen. So that means in this case, the sulfur is being oxidized, right? And by default, that would mean that this guy is actually being reduced. So you can also, again, still look at the charges here. That's still 0. That's really oxygen, which is -2. Oxidation state, that's sort of what's happening. Down here, the copper has how many oxygen? Copper over here has how many oxygens? Over here, they have none, right? On this side, on the right. So copper has lost oxygen as it went from left to right, which is this definition. It is the copper here that is being reduced, and it is the hydrogen that is being oxidized. So sometimes you could look at the hydrogen and oxygen. And again, in organic chemistry, that's pretty easy. You could also look at the metal that's here to help you. The metal, that is copper 2, by the way. And that is copper by itself, which has no charge. That means if I just look at the copper, it is starting at +2, which is over here, and ending at 0, right? And it is being reduced in that case. If you look at the copper, and that is what we determined by the other method as well. So in this case, you actually still look at the metal that's there and figure it out in that sense. Any questions on that? Again, I would say at this point, electrons being gained and lost is probably the definition of oxidation and reduction that we'll see the most, but we definitely will see the other definitions when we get into organic chemistry in terms of gaining or losing hydrogen. And there's our hydrogen, which is sort of what I said on the previous slide there. All right. Now that we talked about sort of redox reactions, as I mentioned before, this is the three main reasons why a reaction takes place. And although there are two big umbrellas of reactions, redox reactions and double displacement reactions, underneath each of those umbrellas, you can more specifically classify a reaction based on what's going on. So let's take a look at some of these reactions and classification. This guy is under the big umbrella of a redox reaction. This is a synthesis or combination reaction. And in a synthesis or combination reaction, it is pretty much what it sounds like. You have basically two things make one thing. Yeah. Combination, right? Comboing it together. That is a more specific classification as a synthesis or combination reaction. So here we go. That is two things make one thing. That is a synthesis or combination reaction. That is two things that make one thing, right? Also, again, a combination or synthesis reaction. Each of these are still redox reactions. We did this guy earlier, right? 0, 0, +1 and -1, right? Oxidizing and reducing. This guy being oxidized, this guy being reduced. Hydrogen by itself, no charge. Oxygen by itself, no charge. -2 for the oxygen, +1 for the hydrogen here. When I look at hydrogen, hydrogen starting at 0 and ending at +1. What's happening with hydrogen? It's being oxidized, yeah? That means by default, oxygen is being reduced, right? We could also see that the oxygen starting at 0, ending at -2, right? Going in that direction. So although it is a redox reaction, there's electrons being transferred. It is also more specifically classified by most people would classify it as a synthesis or combination reaction, as we have two things make one thing. Question on that there. Now, the opposite of that is a decomposition reaction. And in a decomposition reaction, it is also a redox reaction. So this also falls under the redox umbrella of electrons being transferred. It is basically the opposite of what we just talked about. You got two things or one thing makes two or more things. So combination, you put it together. Decomposition, you break it apart. Yeah. And that's what we see here. One thing makes two things. One thing makes two things in each of those cases. And that is your classic decomposition reaction. These are still redox reactions. So I'll just look at the bottom guy here. Mercury is +2. Oxygen is -2. That is 0 and 0 for each of those as they're by themselves. So if we look at the number line here to prove it is a redox, Mercury started at +2 here, ends at 0, which means mercury is actually being reduced, right? The oxygen started at -2, which is over here, and it ended at 0, which is moving in that direction, right? And that means that, whoops, I missed it. The oxygen is being oxidized in this case, yeah? So the oxygen is being oxidized. The reduction is happening on the mercury. It is a redox reaction overall. There's electrons being transferred. But again, most people would use the more specific classification of this being a decomposition reaction. Yeah. Question on that there. Continuing on with our classification, we could have a single replacement reaction. And a single replacement reaction also is still under the umbrella of a redox reaction. So how do you know it's a single replacement? You have one of two options. You have something that is by itself, has no charge, like a metal, and it reacts with something that's an ionic compound. that are made up of ions. Metal that does not have a charge is 0. But when metals do make a charge, what type of charge do they make? Positive or negative? Metals will lose electrons and become positive. So what happens in this type of reaction is this metal that does not have a charge will come in and kick out the guy that has the positive charge. And it's at that point that the guy coming in this case, this guy, will gain a charge and will make a new ionic compound as it gains a charge. This guy that it replaced will come out by itself and have no charge, basically. And that's because electrons are being transferred. That's how they kind of change charges. You could also do this with a nonmetal. So if this was a nonmetal, this nonmetal would react with this negative guy, because that's normally what it would make. And it will kick out that guy that has no charge and make a new ionic compound as well. In order for this reaction to actually take place, whatever is coming in, like this guy that's coming in basically, it needs to be more reactive than what it is replacing. So for example here's how we can see it. That is something by itself, like a metal. That is an ionic compound, basically. This guy is going to come in and kick out the positive guy. When it does so, hydrogen comes out by itself as hydrogen gas. That's how we find hydrogen by itself, right? It's a diatomic molecule. The zinc will then gain its normal charge, which will then be a +2 charge, yes, which will hook up with the chloride, which is a -1 charge. And that is how we get to our zinc chloride that is made, which is a new ionic compound. So that is a single replacement reaction. It is also still a redox reaction. We will just look at the zinc. The zinc on the left is 0. The zinc on the right is +2. What's happening with the zinc? It's being oxidized. In this case, it is the hydrogen, actually, that's 0, +1 on the left, and ends at 0. It is the hydrogen here that is actually being reduced. What's happening with the chlorine? What's the charge on the chlorine on the left? -1. What's the charge of chlorine on the right? -1. Nothing's happening with the chlorine. It is what we call a spectator ion. It's just hanging out. It's floating around the solution, having a good day. But what's really happening here in terms of our electrons is zinc giving up its electrons to the hydrogen on the left, and the hydrogen accepting the electrons and becoming H2 on the right, and the zinc, when it loses those electrons, becomes positively charged on the right-hand side. That's ultimately what is happening here. So that is a single replacement reaction or displacement reaction, and that is still a redox reaction that's happening, but again, most people would classify it as a single replacement reaction. Now, the other types of reactions are double displacement reactions. And that is the big umbrella. And what happens in a double displacement reaction is you actually have 2 ionic compounds. So you have 2 ionic compounds. That is how you know it's a double displacement reaction. You look on the left-hand side of the arrow, you see 2 ionic compounds there. And whenever you see 2 ionic compounds, what always happens is the 2 positive guys switch partners. So they do like a little switch of partners that happen. And they make 2 new ionic compounds on the other side. And that is the big umbrella of reactions, which is double displacement. Double displacement accounts for making a solid and making water, which is 2 of the 3 reasons why this reaction takes place. What will happen is one of these guys may make a solid, which is known as a precipitate, or one of them may end up being water, which is really what will happen in this case. So let's take a look at the precipitation reaction. The precipitation reaction is a more specific classification of a double displacement reaction that's happening. How do I know this is a double displacement? That's an ionic compound, negative guy. And the guy next to it is also an ionic compound, positive and negative. So automatically when I see those two ionic compounds together, I know it's a double displacement reaction. This potassium will then go hook up with the nitrate. And that is how we get to this guy, right? Now the barium will then go hook up, and that is how we get to this guy. The result of the barium and the chromium coming together forms what type of thing? Forms a solid, which is why this is referred to as a precipitation reaction, because it formed a precipitate. A precipitate is a solid that is formed from the mixing of like two solutions. You mix two solutions together, the ions floating around go find each other, two of them come together and actually come out of solution solid, and that is what is known as a precipitation reaction. So overall, this reaction that we're looking at is a double displacement reaction, but more specifically, because it made a solid, is more specifically called a precipitation reaction. Question on that. So again, here we see that double exchange happening where our positive guys are switching partners, and again, making two new ionic compounds on the other side. So that is always how you recognize it. That's how you recognize a double displacement reaction different than a single replacement, because in a single replacement reaction, you only have one ionic compound and something by itself. This is the only type of reaction where you will be starting with two ionic compounds, always going to be a double displacement reaction, and more specifically, could be a precipitation reaction. Now, if we take this two guys together, this is what is known as hydrochloric acid, which is an acid, and KOH is potassium hydroxide, which is a base. That is an acid and base reaction. And whenever you make an acid and base together, especially a strong acid and a strong base together, you always form water. You remember that water is one of the three reasons why a reaction takes place. So ultimately, that is the reason this reaction is taking place, to form water. And you will form what is referred to as a salt. A salt is an ionic compound, like what we have here. So where does the water come from? The water always comes from the hydrogen from the acid and the OH from the base. That makes water. And that's ultimately what is happening in this reaction. It is the H plus from the acid finding the OH minus from the base, water. And that is what is called an acid-base neutralization reaction. They call it an acid-base neutralization reaction because basically you're making water. Yeah. This is also a double displacement reaction. And to prove that it's a double displacement reaction, that's a positive negative. That's a positive and negative guy. When the H switches partners, H and OH come together to make water. The K and the Cl come together to make your KCl. So this is more specifically classified as an acid-base neutralization reaction. It is broadly classified as a double displacement reaction. It falls under that category. Question. All right, we just have one more to look at to finish it out here. So let's finish here, which is a combustion reaction. So a combustion reaction, I would say that most people would talk about an organic combustion reaction. And that's what we see in both of these examples. An organic molecule that basically is carbon, hydrogen, or oxygen, like what we have here. You react it always with O2, and you make CO2 and water. So if you have an organic combustion reaction, like when you light your Bunsen burner, methane comes out, oxygen in the air, a little spark, you get fire, like methane, propane, butane, right? All those things are organic compounds. They make fire and a lot of energy. This is your classic organic combustion reaction. With that being said, combustion reactions do fall under redox reactions. And a more general definition of a combustion reaction is this: you simply just need oxygen, and you could classify it as a combustion reaction. That means when we look at this reaction that we saw earlier, magnesium plus oxygen makes magnesium oxide. This is a redox reaction, as we saw earlier, right? We got electrons being transferred. That is two things that make one thing. Means it's also a combination reaction, right? That is also oxygen, which means you could classify it as a combustion reaction. That same reaction could be classified 3 different ways depending on what you're looking at. I would say most people would classify this as a combination reaction. After that, most people would probably call it a combustion reaction in most cases. Summarize our reactions and ways of classifying. We have a redox reactions, which are for our transfer of electrons. More specific classifications of redox reactions are a combination reaction, our synthesis. It is a decomposition reaction. It is a single replacement reaction. And it is a combustion reaction. All those more specific classifications fall under the umbrella of redox, and in every single case, they are all transferring electrons. That's basically what's happening. Your other big classification is your double displacement, which has more specifically our precipitation reaction, which means you made a solid, and our acid-base reactions, which means you made water. And again, that pretty much accounts for all 3 reasons why a reaction takes place: transfer of electrons, making a solid or precipitate, and water being formed. So again, they all more specific classifications fall under the big 2 umbrellas of either it's a redox reaction that's really happening, or it's a double displacement reaction that's happening. Any questions on that there? All right, we will lay that up to